Welcome to the second part of the 18th chapter on axioms and uniform substitutions in the Logical Foundations of Cyber-Physical Systems textbook. We're still in the business of worrying about succinct approaches for soundly implementing rigorous reasoning for hybrid systems, so we're still in the engine room of hybrid systems proving. But now we're moving on towards the part of that where we get down into the weeds of what happens with differential equations. And of course, we will still exactly exploit uniform substitutions for the job. Now let's worry about differential axioms and differential equation axioms and all these, how they are best rendered in uniform substitution. And remember, of course, the reason to do so is best illustrated with the axiom schema for differential equation solving, which is rather complicated because it says that a property of a differential equation is always true after running the differential equation if and only if at every time t is the solution y of this differential equation at time t when assigned to x such that it satisfies the post condition. But that axiom schema is highly schematic. It needs the variable t to be fresh. It needs the solution y to actually be the solution of this differential equation with actually y plugged in for x in the term theta. And that differential equation solution shouldn't just be any arbitrary solution, but it should be the one that starts at the initial value that is written down by the variable x. And it needs to cover all the cases of the solutions parametrically in case there's multiple of those representations, depending on the function of the initial value. And x prime also had better not occur free in the post condition. It's just too subtle to check all of those side conditions. Instead, we're completely abandoning, even though it's sound, this axiom schema as we're moving on to a purely axiomatic approach, where we exploit uniform substitution to make this happen. Uniform substitution says that if a formula phi is valid because it has a proof, then a substituted version of it is also valid, where the uniform substitution replaces all occurrences of predicate symbols of arguments with a specific formula of the same kind of argument plugged in, remember, recursively by using uniform substitutions, while replacing function symbols of arguments by terms of the arguments, again plugged in recursively by uniform substitutions, and replacing program constant symbols by concrete hybrid programs. For example, this was one of those uses of the uniform substitution. Replace the program symbol A everywhere where it occurs, but the same program, for example, a purely discrete one, replace the program symbol B everywhere where it occurs by another program, for example, a differential equation everywhere where it occurs, and replace the predicate symbol P by a concrete formula, for example, x greater than 0 everywhere where it occurs. Now, what about differential equations? Well, the axiom for solving differential equations is very useful, particularly in intuition land, but we didn't really need it. Remember, in the 12th chapter of the textbook, where we worried about differential ghosts, that we find out that we can indirectly work with solutions even if we don't have a solution axiom for the job. And in fact, in the previous chapters for that, we also understood that differential invariants, differential cuts, and differential ghosts are very useful also for proving other properties of differential equations that we have no chance at all of proving by solutions. Differential invariants, differential cuts, and differential ghosts are extremely useful proof rules if we can implement them based off of our uniform substitution principles now. Then all the advanced sophisticated reasoning of part 2 of this textbook will be readily at our disposal. Now remember, these proof rules package up informations coming from corresponding axioms in useful ways. For example, the differential invariant axiom, the differential cut axiom, and the differential ghost axiom. So in fact, it suffices if we just render those differential equation axioms in uniform substitution style. And here's the answer, but it's better to develop it one step at a time. So the differential weakening axiom says that a postcondition is always true after a differential equation if and only if it's being implied by the evolution domain constraint is always true after the differential equation. So, because a differential equation limited to an evolution domain constraint Q of x, which is this region here, can just never go anywhere where Q of x isn't true. So, the least thing we definitely know while the differential equation is evolving is that, I guess, the evolution domain constraint is true after it, from which this slightly simpler version of differential weakening, in fact, the more useful one derives. But how we render this in uniform substitution style is, of course, that because we don't know what differential equation it is that we're talking about, we need to mention a function symbol f, and it needs to get an explicit license to depend on x. So it needs to explicitly mention x, because otherwise no substitution for f would ever be allowed to mention x here. Likewise, the evolution domain constraint is a predicate symbol because we don't know when it's true or false, but we do know that its true value might very well depend on the value of x. In a sense, that's the whole point of an evolution domain constraint, that of course its true value changes while the differential equation is running. And the postcondition, of course, also is a predicate symbol because, well, it's true or false, and its truth, however, depends on the specific value that x is. And then we've correctly rendered this differential weakening axiom in uniform substitution style. That this axiom is sound is an obvious consequence of the fact that the axiom schema we saw in chapter 11 on differential invariants and proofs is sound, because this is just a specific instance of it. But what we now need to understand is, have we lost anything? And in order to make sure we understand that, let's set up a substitution that is replacing f by an argument. And now, for the moment, imagine I wouldn't have given it an explicit license to depend on x. Then f would be a function symbol with no arguments. And then if we try to substitute it with, for example, x squared, this would be disallowed, because in the context where we would like to replace f with x squared, do we not get permission to talk about x, because we're in a context where x is bound, x is changing, because x has a differential equation, x prime equals something, so apparently its value is changing. And that's why it is, of course, very important that the function symbol gets an explicit permission to depend on the argument, so that we can instead say, f of the argument is replaced with take the argument and square it, for example. And well, in fact, probably we should also substitute q in some way, q of an argument. Let's say take the argument and compare it to less or equal 10. And probably we should also take the postcondition, which is a predicate symbol of an argument, and substitute it with something. So, for example, let's say that the argument is positive. And then if you run this uniform substitution over the differential weakening axiom, then what we were going to get is x prime is x squared within the evolution domain constraint where x is less or equal to 10. And the postcondition being, well, is x then positive? And of course, if and only if dot 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 like that on the right hand side. Moving on to the differential cut axiom. This one enables us to show that we can edit the evolution domain constraint with an extra conjunct r of x. Well, if we have already proved that r of x is always true. So hold on a second. So that means along a differential equation that is limited to remain with evolution domain constraint q of x, so here, right, is a postcondition p of x always true if and only if that same postcondition is always true within the evolution domain constraint that's limited to the conjunction q of x and r of x, if we already know that r of x always holds true after the differential equation anyhow. So if we are initially limited to the green region, what we prove for this condition here, that we can never leave the blue region R, then of course we can limit the domain to the conjunction of the two, where q of x and r of x are true. So only this region is now necessary for us to explore. And of course, remember, we might want to do differential cuts repeatedly if we find multiple of those arguments, and then literally cut them out of the state space. Remember, differential cut is like a differential modulus ponens k. And of course, the rendering as a uniform substitution axiom, again, just says, well, we don't know what concrete truth values the evolution domain constraint, the post condition, and the extra constraint added to the evolution domain constraint have, but they are true or false in certain states as a function of the value of x. So these are correctly rendered in uniform substitution style. And again, we can simply start replacing things. For example, we could say, the new thing that we would like to prove about a differential equation is that the argument is never bigger than 100. Right? And so that would then fork off a new question. Is it indeed true that the differential equation evolves only within the region where the argument, so in this case, x is at most 100, so that will be the question, is x less than 100? And after we have proved that, over here we might as well write in, I guess from now on we can assume that x is at most 100 because we just first proved it to be less than 100 a moment ago. And notice also, if, for example, our substitution would like to show a new post condition that doesn't say that the argument is bigger than 0, but that instead says that the argument is bigger than y, then this is permitted because even if R apparently only has explicit license to depend on x, we can still ask the uniform substitution to sneak in an extra free variable y, because in this context, and in every other context where R of x occurs, is y, the fresh variable y, not bound. So we can still refer to whatever initial value y had before this reasoning, and it will be the same that the value y has in these positions here. Remember that the differential invariance axiom allows us to show that a property is always true after a differential equation, if and only if it's true right now. Well, if we pass the test of the evolution domain constraint, otherwise the two aren't really equivalent. Provided we also show that the differential of the property is always true after the differential equation. And remember, for the prime, we wish we could think of time derivative, but remember the time derivatives aren't always well defined, especially not in isolated states that we're talking about. So instead, in chapters 10 on differential invariance, have we identified that understanding this as a differential, so something that talks about local change in the local state, is the better way of understanding them. But we still had a way of making sense of this as a property that tells us whether locally p of x remains true. And if this is the case always after running the differential equation, then I guess sort of intuitively, we saw it rigorously back in chapter 10, if p of x starts out true, then if it also has a trend to remain true, then it always will remain true. And of course, if it isn't currently true, it can't always be true in the future. Well, unless, of course, the evolution domain constraint is false, in which case both of those cases are equivalent because of the presence of the test. Now, if we run a uniform substitution over it, we can, of course, say, as a concrete replacement for the predicate symbol p, please ask the question, is the argument less than 100? Yeah, that's fine. But are there any limitations to this? Well, for example, what we can't do easily is ask, is the argument less than x prime? And why is that? Well, because x prime, that would be identified as a new free variable that the uniform substitution is trying to sneak in. And that doesn't seem like a problem over here because x prime isn't changing, but it very much seems like a problem over here because if in this context we're trying to introduce a free variable x prime, then x prime is being bound because remember a differential equation is not just changing x but also x prime because x prime is f of x. And so we don't have explicit permission and also cannot generate a free permission to have it depend on x prime. And this is actually, what is that? Is that a deficiency of how general our axiom is, or is it important for the soundness that we can't just sneak in x prime in the middle of the uniform substitution here? It turns out that's actually very important for soundness, that we aren't allowed to do that. And the reason is, here is the value of x prime guaranteed to be f of x, because we're after a differential equation x prime equals f of x. But over here, what's the value of x prime? Well, I just said a moment ago, we're not after a differential equation x prime equals anything, and we're not changing x prime. In other words, here in this position, will x prime refer to whatever initial value the variable x prime happens to have had, and of course, we have no way of knowing what that might be. In other words, here and there will we be referring to completely different values of x prime, which would be unsound. In other words, in uniform substitution, it is actually easier to write down in unambiguous style what is it that things can depend on explicitly, the x's, and what parts they cannot depend on. Now, for the differential effects axiom, remember that's the one that enables us to tease out the effect that a differential equation x prime equals f of x has on the x prime value, namely that along this differential equation while we're following it, apparently x prime always has to have the value f of x, because that's what it means to follow a differential equation. Then the differential effects axiom makes this clear by saying a formula p of x prime is always true after such a differential equation x prime equals f of x, if and only if, after the same differential equation, p of x prime is true after we have put the value of f of x into the variable x prime by an assignment, which remember is a pseudo assignment because it has that value already anyhow. But the point is, now we have it explicitly readily available for the rest of the proofs. And what would have happened in this uniform substitution rendering of the differential effects axiom had we suppressed x prime here? What if we hadn't given it an explicit license to depend on x prime? Well, in that case, if we were trying to run a uniform substitution over it that, for example, replaces p of the now one argument with compare the argument to x prime, say, that's not extremely exciting, but let's do it anyways, then that would, of course, clash, because we just talked about it a moment ago. In this context, is x prime changing, so we can't sneak it in extra as a free variable, which means the only replacement we can make for the predicate symbol p are things like is the argument bigger than y or something like that, and that's all good, but the point is then it would be utterly useless to do this in a context in which we're explicitly calling out that x prime has the value f of x by an assignment, because this cannot have an effect on any formula that we have dropped in as a replacement here, because it wouldn't be allowed to mention x prime. In other words, for this axiom to be useful at all, is it of course extremely important that we give the predicate symbol explicit license to depend both on x as well as on x prime. Moving on to the differential ghost axiom. This is rendered in uniform substitution style as follows. Remember what it says. It says always after a differential equation x prime equals f of x is a postcondition p of x true if and only if there is a value for the variable y, which is a fresh variable y, such that in the joint differential equation system x prime equals f of x, as well as a newly made up differential equation that we made up arbitrarily, y prime equals a of x y plus b of x, is the postcondition true. So the old dynamics we augment with the fresh dynamics that we dreamed up in a way that we liked to make sure that our proof makes progress. And remember, the overall goal is to make sure that we can then identify nice invariants of the old and the new system together that were impossible to even express previously in the old system, for example. And the point is, the differential ghost principle was only sound, well, first of all, when the new variable is actually new, right? And that's given because this is not an axiom schema in which we need to say, please don't use it with the same variable x that you used for y, because it's a concrete formula, and for the concrete formula, just read that apparently the variable x has an entirely different name than the variable y, so this is built in, as opposed to some side condition having to rule abuses out. And likewise, for even more subtle reasons in the differential ghost axiom, was it very important that this new differential equation that we're sneaking in didn't in crazy ways explode in finite time, because that would of course make the reasoning principle incorrect. And here we can do this very easily, exploiting uniform substitution by saying the new differential equation has to be of the shape y prime equals a of x times y plus b of x. And both a and b have explicit permission to depend on the old variables x, but the new variable y only occurs in a specific linear form. And in particular, look what happens when we try to replace the function symbol a of an argument by, for example, take the argument and do it to the cube. Well, that we can easily do, but if we try to also add y, for example, into this, then during a uniform substitution will, of course, y be identified as a fresh free variable that we're trying to sneak into this context, and we would be forbidden from doing so here because, hey, wait a second, that's in the middle of a context of a differential equation for y, so apparently y is changing. We can't put in a free variable into a context where it would be bound because we would go to logic jail. And likewise, the same thing would happen if we were to try to sneak in, for example, y square into this constant term here. That would also be forbidden and identified as a bad use of that. Whereas in comparison, it's perfectly fine if instead of trying to sneak in y as a variable, we sneak in a different variable z, and even z power 55 if we really want to, because for another variable z, that's now very, very fresh, right? Okay, cool, but we're using it only in the context in which x and x prime and y and y prime are changing here as well, but z is untouched, so we get to talk about it if we so want to. Now, the solution axiom in general we didn't want to have in uniform substitution style because the relationship of the differential equation to its solution is kind of sort of non-obvious in general, but there's an important way in which differential solution axioms are actually very easy to write down, and that's if the right-hand side of a differential equation is a constant. Well, in that, of course, in that case, do we not have a fancy differential equation that we're following? Well, we're following a very easy differential equation with a constant slope. We don't know what the slope is, but it's going to be a constant function symbol, c with no arguments. And in that case, of course, is the solution exactly take the old initial value of x and add constant multiply with time to that. And in this case, it's very easy to trace a differential equation solution axiom by saying always after a differential equation x prime equals some constant c within an evolution domain constraint q as a function of x is a postcondition p as a function of x true, if and only if for all times t greater or equal 0. Remember, t is a different variable than x, so this constraint is also by construction as opposed to by side condition. Then if for all intermediate times s between 0 and t, the evolution domain constraint q is true for the value that we have at time s, this intermediate time, which is the value x plus constant multiplied with intermediate time s. Well, if that's true for all of those intermediate times, then at the end time t is p of x true after we assign the value of the solution x plus constant multiplied with time to the variable x. And again, if our uniform substitution were to inadvertently try to replace the function symbol c of no arguments with x, right, then our uniform substitution would say, wait, hold on a second, x is a free variable. If I try to sneak this in here, right, then that would be x prime equals x if we shut off the conscience of the uniform substitution algorithm. But in that case, of course, over here what we get x is x plus x times t, and that very much is not at all the solution of the linear differential equation x prime equals x, because remember the solution of that actually is an exponential of time, right? So fortunately that is being ruled out as well by the fact that c is a constant symbol. So for example, we can say the uniform substitution should please replace c by another variable y that isn't changing, or by, for example, 92, right? But not by anything else. Now let's use this for some good. For proving properties of differential equations that we can't just solve, but we can still prove by differential invariance, for example. So if we would like to prove this property by differential invariance, we point to the differential invariance axiom and ask uniform substitution to choose the appropriate instance, which says if it's true in the beginning, then it will always be true. If you can convince ourselves that the differential is always true, for that we now point to the uniform substitution instance of the differential effects axiom, which will tease out that the value of x prime apparently is x cubed and can be assigned to that. Then in this context, do we need to worry about what's the differential of this formula? Okay, let's do this by context congruence reasoning by saying, well, first equivalently rephrase this red formula into some equivalent green formula. We tramp that one up and prove that it's correct. And then, of course, in this context, is it fine to replace the red formula with one that it is equivalent to, the green one, and continue the proof down here. First, let's worry about this side. How does that work? Well, so that prime applied to a greater or equal will, of course, prime both sides. The prime of 1 is 0 because, of course, the value of the number 1 doesn't change over time, so its derivative will be 0, whereas that gives us the differential of x times x. On this side, of course, the thing stays, and now we say, in the context of a greater or equal comparison, will those two be equivalent if, for example, the terms themselves are equal? Then, of course, if they're equal, they're either both greater or equal 0 or none of them are. In order to prove this, we can, for example, change the differential of a term that happens to be a variable is equal to the differential symbol x prime. Easy observation that we've seen a long time ago, which also is easy to express in uniform substitution style. And then, in this step is the one I wanted to make explicit. Here, this equality follows, for example, by explicit uniform substitution from the Leibniz rule for differentials, written down explicitly like this: f of x multiplied g of x and the whole thing prime. This is the same of f of x prime times g of x plus f of x times g of x prime. Then all we need to do is replace f with x and also replace g with x in the entire context, and then have a proof here. Remember where we came from? We came from a proof that the red is equivalent to the green, which we now proved, so we can mention the green in place of the red here. And then this branch, do we then say, oh, the Gödel proof rule can get rid of the box in the beginning. There it's gone. Remember, it's important that any formulas in the antecedent are also gone, because we can't get to assume them any further. But then we have the assignment to the prime symbol, which we can, of course, by a uniform substitution instance of the assignment axiom, turn into this, and that easily proves by arithmetic, because x power 4 plus x power 4 is definitely greater than 0. So this has a proof. The only part that is a little bit annoying is that at this point, do we kind of have to guess what the output is in order to be able to fill in this proof. And that we can do a little bit better later on. But observe, we've used those axioms for differentials, which are equations of terms that happen to mention differentials. So, for example, the differential of a sum of two function symbols is the sum of the differentials of the function symbols, and likewise a Leibniz rule, where a function symbol occurs that has license to depend on all the variables, because we might want to use them all. And also very cute, rendering for function symbols C of no arguments, that their differential is always 0, is easily stated in uniform substitution style as well, because a uniform substitution that would try to replace the function symbol C with, say, the variable x multiplied with itself, that would be highly forbidden, because the uniform substitution would notice that there's 3 variables in it that we're trying to sneak into a context with primes, and we can't do that because, of course, the value of x times x prime very much not just depends on x, but also depends on x prime, and in any way it depends on a lot more stuff than the arity 0 function symbol does, which visibly depends on the values of no variables, so can't possibly have a spatial derivative. And these derivation axioms, of course, directly follow from the more general schematic versions that we've seen in the past as well, except it's possibly a little bit easier to understand what it means exactly for this to be a function symbol, because it visibly has no arguments. Now, summarizing, these are the differential equation axioms that we've identified in uniform substitution style. They're all very, very tame and very explicit about what specifically they're allowed to depend on, and likewise the differential axioms. Let's use them for some good. In particular, let's understand the congruence reasoning a little bit better that we were doing at this point for terms and at this point for formulas. How does that work? Well, we've already seen that congruence for terms means if f equals g, then predicate symbol p applied to f is equivalent to predicate symbol p applied to g. And that, by uniformly substituting f with x times x prime and g with that green term, gives us license to derive in one step by uniform substitution applied to that congruence reasoning proof rule this equivalence that we've used. Likewise, by sort of complete analogy, if two formulas p and q are equivalent, then also in any context c is c of p equivalent to c of q, and that's kind of morally sort of the same as that congruence reasoning rule, except here we're dealing with equivalences of formulas, so that's a formula applied to a formula precisely. That's the only slight complication of it. It is easy to make this very precise, but you will do just fine in using it intuitively. For example, in this context here, do we say the formula context applied to the argument is that formula into that place either the red or the green formula will have to be put in. The red one is the one we get for the replacement of p, whereas the green one is the one we will get as a replacement of q everywhere, also here and here. You can make them very precise, for example, in the article in the Journal of Automated Reasoning 2017. But the one thing that was a bit annoying about it is, as we're conducting the proof at this moment, when we were trying to form the differential of something, that we kind of have to guess the answer and then continue the proof. And we can do better than that, because we can, for example, exploit uniform substitution also for other styles to go parametric, because we can certainly at this moment say we don't know what the differential of this exactly will be, but of x times x will be something that's mentioning x and x prime. If only we had a construct that tells us it's something that depends on x and x prime and some real number of that. And of course that's a function symbol that we can say some result j of x and x prime will, being greater or equal to 0, will be equivalent to that. And that will give us this formula over there. And then we can continue the proof. For example, here, apply the Gödel reasoning principle and assign to it to show that the remaining question is whether j of x and x cubed is greater or equal to 0. And on this side, can we continue the proof a little bit as well, reasoning on that side and on this side, and then ultimately say, I think I got it. I know what I need to plug in for j of x and x prime, and that's, of course, we're plugging into an entire proof by uniform substitution. Once you've found out the answer later on, it's just, again, one reasoning application of the uniform substitution on the entire proof, which will replace this here by x cubed x plus x cubed, and on that side we'll replace it as well with something that will then be easily proved, as we saw before, as essentially a uniform substitution instance of the Leibniz rule for differentials. But we can do it a little bit better as well, because we don't even need to guess that this parametric answer will be of this shape. We can also go a little bit more unconventional once we identified that uniform substitution and reasoning is sound, by instead saying, well, we don't know what the answer is. Why don't we construct it? Why don't we construct it out of, for example, a trivial answer that apparently this will soon depend on x times x prime. What can we prove about x times x prime being equal to? Well, we can certainly prove that it's equal to itself, which is true, but not very exciting. But this has a proof. Great. Now let's take this proof and simply develop it forward until the two meet. Right? We've been doing the proof backwards. We all of a sudden temporarily do a forward computation proof. So now we investigate this side and say, what is it equal to? Well, by direct use of the Leibniz differential rule, is this, of course, the same as x prime times x plus x prime, and then the differential of the variable is, of course, the same as the differential variable, period, so that's the same as x prime. And we've identified that this equals that, and now it's an explicit term that doesn't have differentials in parentheses anywhere, but it's sort of flat and primitive, which means, of course, one of them will be greater or equal to 0 if and only if the other one will be, and then we can again package it up into the shape that we need. And after having computed in this way what the answer is, we can now continue the proof on the other side in a backwards fashion and say, having computed the answer, constructed it by proof, let's just continue concretely with the answer until we get a proof directly. So the point is, there's different styles of doing proofs, and once we identify what correct reasoning is, you should absolutely have the courage to use it in a courageous way to say part of it will be constructed backwards, part of the proof will be constructed forwards, and the rest of the proof resumes backwards. Once we identify what sound reasoning is, it's okay to combine it in flexible ways. The point is that uniform substitution as one proof rule gives us a lot of flexibility because we'll once and for all deal with all the subtleties of plugging in things for others and respecting variable boundaries and things like that. But uniform substitution had this conditions that it had to check at every moment in time whether the free variables are intersecting the bound variables, the variables of the substitution intersecting the bound variables of each of the operators, because if you bind a free variable, you go to logic jail. But that's cool. It's the only place where we needed to know anything about free and bound variables, but I guess we still need to define what free and bound variables are for differential Lemming logic. Let's do so. The correctness properties that they need to have is that bound variables are such that these are the only ones that change, which means if we're running a hybrid program alpha from an old state omega to a new state nu, then the old and new state agree, except possibly on the bound variables. That means they agree on the complement of the bound variables. Only the bound variables are written to. Things that aren't written to can't be changed. Think of it this way. If you have a program that's assigning to the variables x and y and z, well, then they might change, but a different variable abc can't possibly change, right? So the old and new state have to agree on that. So only the bound variables change. The coincidence lemma is the dual to that, telling us what correct free variables are. If we have two states which agree on the free variables of the term, then if we take the term and evaluate in the one state and take the term and evaluate in the other state, we ought to get the same real number back. And likewise for formulas. A formula is true in one state if and only if the formula is true in the other state, as long as the two states agree on the free variables of the formula. Of course, a term that talks about x and y square and whatnot can only depend on the values that x and y have. It cannot depend on the values that variables a and b have, because they're not even mentioned, likewise in the formula. Right? Formula is a little bit more subtle because it might quantify a variable for all x squared greater or equal to 0. That formula doesn't really depend on the initial value of x because we're overwriting it. That's why we will be defining that. For programs, it's even a little bit more subtle. It goes as follows. If we run a program from an old state to a new state, then certainly by the bound effect lemma do we know that these states will have to agree on the complement of the bound variables, because only the bound variables at most can possibly be changing. But we also, in the coincidence lemma, know that if the old state omega had a similar state omega tilde that agreed at least on the free variables of the program alpha is reading, then if there was a run of the program from the old state omega to a new state nu, then there also is a similar run of the program from the old state omega tilde to the new state nu tilde, such that, again, these two are similar. So to similar old states go to similar new states, which agree on at least those free variables, in fact, on even anything else that they already agreed on initially, and also on all the must bound variables. We'll get to that in a second. Only bound variables change, and only free variables determine the truth of a formula, determine the real value of a term, or determine the transition behavior of a program. But let's define it. How do we correctly compute the free variables of something? Well, so what are the free variables of a term that happens to be a differential? Well, I guess these ought to be the free variables of the term. Hold on a second, except not really, right? Because if theta mentions x and y, then x and plus y prime will not just depend on x and y, but also depend on the x prime and the y prime. So that means that needs to be the free variables and the free variables in all their primed versions as well. What are the free variables of a predicate symbol? Well, of course, the predicate symbol itself doesn't have any free variables because it doesn't depend on anything, but the arguments do. So we just take all the free variables of all the argument terms. That was easy enough. Yeah, well, free variables of a conjunction, of course, there ought to be just the free variables of either side, union together. Free variables of a quantified formula. Well, these are the free variables that the formula has, except one variable isn't actually free in the quantified version of it because, well, x is being bound. We're overwriting whatever initial value x had with all the real numbers or one real number anyway. We're no longer interested in the initial value that x used to have. And I guess sort of like that for the modalities, right? So for the modalities, do we also worry about the free variables that the post condition has? Except some of them we're no longer worrying about, right? Sort of, right? The ones that the program is writing into, in analogy to what the quantifier is writing into. And which are those? Well, I guess something like the bound variables of the program. These we can remove. But, of course, when computing and writing to variables, the program might read other variables, which are, of course, the free variables of the program. So these ones we absolutely need to throw in. Right? And then, of course, if a program is reading a variable in order to compute a new value for it, then it's still reading it first. So in other words, we only remove the bound variables from the program. And it will turn out, think about it, that this isn't quite right. But let's go ahead. What are the free variables of the program symbol? We don't know what the program symbol is interpreted with, so I guess it could read anything. So that will be the set of all the variables. For an assignment, it's just whatever the right-hand side is reading. For a test, it's just whatever the formula is reading, so has a free variable. For a differential equation, oh, I know. We're reading the initial value of x, right? And then anything that the right-hand side is depending on and anything that the evolution domain constraint is depending on, we're reading as free variables. For a choice program, it's any variable that's free on the left-hand side because we might be reading it by running it, and every variable that's free on the right-hand side. What about sequential composition? Well, anything that the first part is reading, we're reading. And I guess anything that the second part is reading, we're reading, except, again, variables that beta is reading that alpha has already written. So I guess we're not exactly really reading them. So again, we can remove the bound variables of alpha, but like so, because if alpha is reading variables first in order to write them, then of course they still need to be removed. And again, there will be a mistake here. We'll worry about it in a second. And what's a loop read? Well, I guess anything that the loop body reads is what the loop is reading, and done with it. Except these aren't quite right, because in a few places they're flawed. And the problem is that a program might write to variables. Well, that'll be very nice, but the program, of course, doesn't write to the variables necessarily in every path that the program could run. Think of the choice, right? We could be writing on the left-hand side, we could be writing on the right-hand side, but we don't have to do both. For example, a program that is like that is this program is reading x in order to write to x, and it doesn't have to do so on every path, because if we run the left-hand side, we are guaranteed to write to x. If we run the right-hand side, we're totally not guaranteed to write to x. In fact, we won't. Yeah? But let's say, like so, on both of those branches, are we guaranteed to write to a different variable z, right? So in that case, z, x, and y are potentially written to, but only z is guaranteed to be written to. And only the ones that are guaranteed to be written to are the ones that are no longer being read in phi. And likewise for the sequential composition case, actually. So, in other words, here we need to apply some caution and go for only removing the must-bound variables, not the ones that might be bound on some path of the program, but the ones that are guaranteed to be bound on every path of executing the program. And also, we're not reading the initial value of x prime. We're only reading the initial value of x. Let's then define those must-bound variables, but first maybe define the bound variables that the uniform substitution needs. Well, that kind of sort of should be actually easier, right? So let's pick on one case. I guess the bound variables of a quantifier, well, I guess x is bound, right? And whatever is bound within phi is also bound in the entire thing, right? And for example, the bound variables of an assignment, well, I guess we're writing to x, so that is definitely bound, right? And of course, nothing in phi that can possibly be bound because we're only reading from it, we're not changing any values. So, in other words, here we go, these are the answers, except in one case we need to be a little bit careful because the bound variables of a differential equation are both x and x prime because both of them are changing, even if the free variables of a differential equation are only coming from x, well, and the ones we read from here, but not from x prime because we don't depend on the initial value of x prime. And for example, non-deterministic choice and sequential composition, just anything that we're bound on either side. And in a loop, just anything we're bound in the loop body. In a program symbol, literally every variable is bound because we don't know what the program symbol's interpretation does. It might change any variable around for as far as we know. Now the must-bound variables, the ones that are written to on every path of the program. And then what's the biggest difference? Well, the difference is if the program has different non-deterministic choices of running, then we don't know what happens. In other words, the biggest difference is that the must-bound variables, the ones that are written to on every path, need to be the intersection of the must-bound variables of the left-hand side and the right-hand side for the case of non-deterministic choice. Because the point is we can't know whether alpha or beta will be run, so only the variables that are written to on both of those paths are written to for sure when running alpha choice beta. And likewise, the must-bound variables of the loop is nothing because we're not guaranteed that the loop will run at all. And also the must-bound variables of a program symbol is nothing because, well, we don't know its interpretation, so maybe it doesn't assign to anything at all. And now we have precisely what we need in order to correctly guarantee that only the bound variables change while the program is running, and only the free variables determine truth. And remember, this is where in a slightly nicer, stronger statement, the must-bound variables are also guaranteed to agree on the final states of the programs because, hey, they're written on every path. They must have been touched. And that's precisely what we need as input in order to correctly implement uniform substitution, which is a straightforward homomorphic computation, but also the free variables and bound variables. They were slightly subtle to come up with, but then they're absolutely straightforward to recursively compute just as a function of the syntactic shape of the formulas, terms, and programs. And what we've developed now is the uniform substitution understanding, in particular for the differential equation cases as well, and the differential cases. But all of them are actually very, very tame. And explicit, for example, here in terms of, hey, we explicitly worry in the axiom what happens with the dependency on x, because if you visibly see it, we explicitly do not have x prime in it because we would notice right away if we were to try to prove the axiom sound with an explicit dependency on x prime. But for free, does the uniform substitution give us without having to think about it, because it's its responsibility, not the responsibility of a differential engineer's axiom, that it would be perfectly fine to replace the predicate symbol with something that not just depends on x, but also depends on z and y and other stuff. And also, remember in the differential ghosts, was it kind of useful to have an explicit mention of the variables and then it be only the responsibility of the uniform substitution to make sure that this explicit dependency is being preserved during the substitution process. And that wraps up rather nicely everything we ever need to know about the uniform substitution for our purposes.